yes, grade 10s. You are hanging out with Looney yet again, and you're with Tracy. How are you?
I'm fine. I'm a little worried and a bit scared right now, but it's okay.
What's wrong?
I think you've had too much sugar, Looney.
No, I'm fine, but what are we doing?
Excited? Okay.
What are we doing
grade
with the grade 10?
Getting back to the science. We're going to do waves and electricity revision today, just like last week. We're going to do some of the grade 10 exemplar paper. All right, so some typical exam type questions on waves and electricity.
Awesome stuff, grade 10s. You heard it, so I hope you guys have all your notepads out and you have your pens to write down the notes. But don't worry, because if you don't have all of that stuff and you do have a Samsung device, either a premium smartphone or a Samsung tablet, then you listen up. We do have our awesome Learn Extra exam revision content on these beautiful Samsung devices. As you can see right now, we've got Tracy teaching on this side and you have your notes, so it's very interactive, guys. So how I got here is that from my library, this is my library. I've downloaded everything from the Learning Hub. So basically, guys, all you need to do is download all the exam revision content from the Learning Hub on Brands, Mindset, Learn. And you see there, all the content that we offer from Mindset is there. Some is for free, some is for R8.37, but don't sweat. Now you say, Looney, but I don't have a Samsung device. We do have a Learn Extra exam revision marathon competition going on. If your friends haven't told you and you don't know about it, all you need to do is download the show notes, guys, and right at the bottom, last page, you have a race number. But if you do have us on Facebook, we might just have a race number lingering on the page, but we won't want to be telling you that now because we want you to download your show notes, get your race number, the entry form, guys. All you need to do is go on to www.mindset.co.za/learn/win. That is where you get your entry form to enter the competition. Remember, you can hit me up on Facebook, on facebook.com/learnextra, on Twitter @learnextra, and you can download all the awesome content from Mindset on www.mindset.co.za. So with all that said, Tracy now is going to take over.
Oh, thanks, Looney. I am worried about it, but it's okay. We'll get through it. We're fine. We're fine.
No, I'm fine.
Seriously, into the marathon. Great. Guys, I would so want fun, but it's okay. I'm a big girl. I can get over it. Anyway, so as I said, we're going to look at electricity and waves, and we're sort of dividing it up over the next few weeks. We're looking at all the different sections. Today was physics. Tomorrow, next week, Wednesday, Tuesday. Maybe it's catchy, whatever Looney has. Next week, Tuesday, we're going to do chemistry again. Then the week after, we're going to do physics, okay? So let's just head right in there, okay? We're not doing it in the order that you're necessarily going to get the questions in your exam, okay? So don't stress about that. Now, the first question we're going to look at is this one. It's actually a really nice question. And it says to us that the diagram below shows two waves, A and B, of the same wavelength, but different amplitudes crossing each other. So now if we look at our waves, let's just highlight them quickly. So we'll do that's wave B, which is now going to become yellow. Okay, so that's wave B. It's got a nice big amplitude. Okay, wave A is the little one that then crosses over there, and that's great. Now with them having the same wavelength, that really does help us. Okay, it means that they go to the rest position at the same time. It's quite nice in terms of the way you can see the way they're crossing, because they're reaching crests together and troughs together, which makes life very, very easy. So nothing difficult about the diagram. Now the first thing they ask you to do is to define the term amplitude. You have to learn definitions. Guys, that's not an option, okay? So start making a list. It's always a good thing to do, make a list of terms and principles and laws and stuff, because those are your easy marks in your exams. Those are always the easy marks. Two marks for the amplitude. Now the amplitude, okay, in terms of our diagram, is the distance from the rest position to maximum height. Okay, so it's the distance from the rest position, the equilibrium position, to the maximum height or the maximum displacement of the wave. Okay, and that displacement can either be positive or negative, depending on whether it's a crest or a trough. So the way we would define it is we would say amplitude is the maximum displacement of the wave from the rest position. Nice and easy. Now they say to us, draw the shape of the resulting wave as the two waves A and B cross. On your diagram, show the resulting amplitude. First part of this question is quite easy because they want the resulting wave. So we look at this and we go, well, we have a crest meeting a crest, so they're going to increase each other's amplitude, okay? So we've got constructive interference. That means, okay, we need to draw, okay, I'll draw it for you hand. You would use a ruler. So I know I'm going to have to increase the amplitude, but now I've got to look at this and go, we've got to be careful here. We've got one, so up to here, that's one wave. Up to there, that's two waves. The original diagram gives me two complete waves. That means my next diagram must give me two complete waves, okay? So one, and there, it's finished, okay? Nice sine wave. But now we get, it says show the resulting amplitude. There are no values on your diagram, okay? So nowhere did they say that that this here is 5 centimeters and that's 2 centimeters, so you know it's going to be 7, okay? But we do know that the amplitude of A is going to be added to the amplitude of B. So watch what we do. Over there, that's my new amplitude, and that's little a plus little b. It's both of them added together. That's what they wanted. That's how you show the resulting amplitude. So now it's one complete, it's one wave, okay, because if this was two water waves that meet like this, they would increase the amplitude of the wave. So it's one line, two waves, two wavelengths, and then the A plus the B, okay? Question 3, which wave property, oops, there we go, is illustrated in question 1.2? I've just said it. Constructive interference, okay? Constructive interference, because it made it get bigger, okay? Constructive interference. Now they ask you to name the principle. What theory did we use? And the principle here is the superposition of waves. Okay, that's the nice fancy term for interference of waves. That's what it is. Okay, next question. Question 2. In the sketch, not drawn to scale, Q represents an object on the surface of the water in a dam. A person standing on a bridge observes Q moving up and down. Object Q rises to the top every 5 seconds. This is important. Every 5 seconds, Q gets to the top of the wave. So every 5 seconds, Q is at a crest. That means this particular value is period. Big important piece of information to get. Also, on the diagram, from this crest to this crest, they give a distance of 1,5 meters. It's the distance between 2 points in phase, which is actually my next question, wavelength, okay? So I know the period and I know the wavelength now. I haven't even looked at the questions. I've just looked at the information given. Now they say to us, define the term wavelength. Once again, it's another definition, okay? Wavelength is the distance between two consecutive points in phase, okay? The distance between two consecutive points in phase. You have to have the word consecutive in there, grade 10s, because I can't just say 2 points in phase, because if I mean 2 points in phase, I could mean between that trough and that trough. Now, they're not consecutive. It must be one after the other. Very, very, very important, okay? Now, in which direction is object Q about to move? Now we start to really see if you understand how waves work. Remember that with the transverse wave, the direction of motion is perpendicular to the motion of the particles. Okay? So the energy moves this way, horizontally, but the particles move up and down. So what you need to recognize about Q is not going to bob along the string. Okay? Q simply goes up and down as the string moves. Okay? As the string moves. Now, the wave has, the energy of the wave, okay, is on its way down over here. So this Q is over here, which I've lost my pen. There we go. Q is here. Q is actually going to move up as the wave goes, because the starting over here, if we look at the energy Q's at this point, okay, the wave has gone up and down, the energy's passed, and Q's actually going to go up. I'm not explaining this well at all. You're looking at me, I'm sure looking at the TV going, okay, Tracy, that makes no sense. Okay. You've got to think of it this way. This is the part of the wave, everything to the right of Q has already gone past Q. It's done. Okay? This is what's coming to Q. This here. So Q is actually going to become what the particle before it looks like on the left-hand side. And the particle before Q is above Q. It's a little bit higher. So Q is actually going to go up, and then up, and then up, and up until it reaches this point, and then it comes back down, okay? So everything to the right of particle Q has already happened to Q. It's already done all of this. Whatever's on the left of point Q is what's still going to happen to Q. Okay, so this is still got to come towards Q, which is why point Q is moving up. It's the easiest way to think about it, all right? Now, oh, that wonderful word, calculate. Calculate, calculate, calculate. This is why we needed the information I looked up earlier. Okay, now earlier we realized that they gave me period. They said it was 5 seconds because a Q rises to the top every 5 seconds, and they gave me wavelength. So let's write that down. Okay, so my period is 5 seconds and wavelength is 1,5 meters. They want frequency, and we look on our information sheet if we can't remember it, but we go, that's fine, because frequency is 1 over period, okay? So it's going to be 1 divided by 5. So we take out our calculators, which we're just going to put on the side there, and we go 1 divided by 5, and you go, oh, but Tracy, that's what you've written down. In a science exam, you never leave an answer as a fraction. So what I'm going to do is I'm going to change the setup of my calculator so that it's on linear display. Okay? If you don't, you can use the ST button. Remember, that changes the display as well. So we've got 1 divided by 5. I need it as 0.2. If it was in mass display, 1 over 5. Okay, we don't want mass display. We want it as a fraction. So 0.2 hertz. Now what that 0.2 hertz says to me is that there are 0.2 waves in 1 second. What the 5 seconds tells me is it takes 5 seconds for 1 complete wave to happen. All right. Now they ask you for the speed of the wave. And we go, okay, that's actually a nice question, because we know that this wave equation says to us that the speed of a wave is frequency times wavelength. That's why we had to work out frequency in the last question. So that's 0.2. My wavelength is 1,5. So we go back to our calculator, okay? And I'm pretty sure that some of you can do this in your head, and that's great. But we're going to use the calculator just to be on the safe side. So 0.2, maybe I should actually put the 2, times 1.5, 0.3, okay? So we get an answer, there we go, of 0.3, but now we've got to remember that this is speed, okay, so we need meters per second. By now, you have done vectors and you've done equations of motion in class, and you realize that that symbol is actually the symbol for velocity, but the question asked us for speed, so we can still use it interchangeably in waves. Because they asked me for speed, I don't need to put a direction in words. I just need the magnitude, and they're not going to ask for the velocity of a wave. They're going to ask for the speed of the wave, okay, because the direction becomes a little bit of a nightmare with the particles moving up and down and doing all sorts of weird and wonderful things. Okay, I think, Looney, it's time for a break.
Okay.
And we'll come back and do some more questions.
All right. Mindsetters, we are going to take a break just to let you know, guys, on our website, we do have the schedule. Now, if you look there and the notes is highlighted blue, that means the notes are available to download. If the video is also red, that means the video is available on YouTube. Just to clarify, Mindsetters sometimes ask, when are the notes? When are all of that stuff? I've just answered you. Blue equals notes. Red equals video. Let's take a short break and I'll see you straight after this. Welcome back, Mindsetters. You're still tuned in with Looney and Tracy, and we do have exam school. So, Mindsetters, remember, we're going the distance together to try and get you to grade 11 next year. So, we're running this very difficult last lap, and we're going to help you guys for the exams. Just to remind you, I see a lot of you have questions about the competition. All you need to do, step 1, download the show notes. Right at the bottom, step 2, you have a race number at the bottom of the last page. What you do with that race number, step 3, www.mindset.co.za/learn/win. That is the link to the entry form. What you do in step 3 is that you fill out your entry form with your race number, follow the steps there. It's pretty simple, guys. And voila, you have entered the competition. Remember, we are in leg 2, because leg 1 was won by Cecil, and you must watch during this week sometime. We will have a lucky draw, and one of you will be an awesome winner of one of those awesome Samsung devices. So make sure, guys, you stay tuned in to all of our live shows. Now I will just...
I'm worried about her. Just gonna put it out there. You need too much sugar at lunch. Just gonna put it out there.
It seems fun when I do the hands, because it's like I'm explaining rugby.
Maybe she's trying to do, like a Jedi mind trick. I don't know. Moving on.
Oh my God.
Anyway, so in the last segment, okay, so before the break, we did 2 questions and they involved transverse waves. Now we're going to do a question that involves longitudinal waves, okay? And remember, longitudinal waves are sound waves. So they say to us that a sound wave produced by a vibrating musical instrument, whatever that might be, like a guitar or a piano or something like that, is represented in diagram 1. So if we look at diagram 1 and we go, okay, well, actually, we've got to be able to identify certain things. So let's just look at what we have here. A is this point here where they're very close together. So part A would be a compression, okay. Now, B is labeling the part that's going from the middle of one compression to the middle of the next compression. And now we've already said that wavelength is the distance between 2 consecutive points in phase. This point on the wave and that point in the wave are in phase. They are one after the other. So B is actually the wavelength of my wave, okay? And this middle part here, which they haven't labeled, but we're going to put it in there anyway, is a refraction. Okay, that's where it pulls apart. Now they say label the sections marked A and B. Oh wait, we've already done that. Didn't even look at the question. So part A we said was a compression, and part B was wavelength. Nice and simple. 2 easy marks. Now they say to us, the position time graph in diagram 2 below represents the same sound wave produced by the musical instrument above. Now, for us to analyze the wave made from sound, we need to translate it into a position time graph so it looks like a transverse wave. And basically what this means is that your position here represents parts where the energy or the particles are getting closer together becomes your crest, where they're becoming further apart, that's your refraction, that's your trough, okay? And we use things called oscilloscopes to do this. They can pick up sound waves and then they translate them into transverse waves for us because it's easier to work with. Because from a transverse wave like this, it's much easier for me to measure the wavelength, it's much easier for me to measure amplitude, all of those sort of things, far, far easier, okay? Now they say name the type of wave represented in diagram 2. Well, I've said that to you several times already. It's a transverse wave, okay? As it stands, okay? Now, 3.2. Which one, X, Y, or Z in the diagram, corresponds to the section labeled A? So let's look at X, Y, and Z. X and Z are at equilibrium positions, okay? Y is at a crest. The crest or the trough can be your compression or your refraction. X and Y would be, and it's very difficult to see in a longitudinal wave, your rest position is here somewhere. It's very difficult to see. It's not point A. Okay, so X and Y cannot, X and Z, sorry, cannot be point A. It has to be Y. Your maximum displacement, okay? Now, this is always the fun question. Now we've got to think carefully about what they say. They say the same note, that means same frequency. Same note means it has the same pitch, same frequency. Is now played on the instrument, but much louder. Decibels, it's louder, okay? Loudness is amplitude. What they're wanting to know is whether you understand how this changes. Now, what that means is on your diagram 2, your amplitude will increase. Loud noises have big amplitudes. Soft noises have small amplitudes. Now, easiest way to think about this is my voice when I'm talking to you has a certain pitch, okay? Everyone hears the same pitch of my voice because that doesn't change. But some of you have your TVs louder than others. So the amplitude of my voice is different, okay? But it's the same notes, it's the same pitch that's coming out, okay? But you hear a different amplitude, different amount of, not energy, it's just the amplitude. There's more, the particles move further from the rest position, okay? Then, a note of higher frequency, but of the same original loudness is now played. Higher frequency means that I have more waves per second. So what would happen is if it's the same note, if it's the same loudness, amplitude's not going to change, but what will happen, let's do it in yellow, the wave's going to do this. It's going to be more often. But it's the same height, okay? But it's more often. If it's more often, the wavelength is getting smaller. Frequency and wavelength, inversely proportional. Frequency gets higher, wavelength gets smaller. Frequency gets smaller, wavelength gets higher. So if I have a higher pitched voice, or if I increase the pitch of my voice, which I can't actually do, because it will just be embarrassing, okay, the wavelength gets shorter. But if the amplitude, the volume is the same, amplitude doesn't change. Okay? So when you're listening to the TV at home, you can hear different pitches, different frequencies of sound. But because your TV sound is set, it's all the same loudness. sometimes it doesn't always feel like the same loudness because of the pitch, okay, because of the frequency and the way we experience it, but it is actually the same loudness, okay? Hopefully we all got that. Sound's going to be one of those sections that's going to come up again. Waves are very important in grade 10s for grade 12 and 11, okay? Next one, the electromagnetic spectrum. So, some electromagnetic waves are listed. UV rays, which come from the sun, well, all of them come from the sun, okay? Ultraviolet rays, infrared rays, radio waves, X-rays, and gamma rays. This one, gamma, okay? Gamma rays are the ones right at the top end of the spectrum with the highest frequency. Very, very, very dangerous, okay? Now they ask you, how are electromagnetic waves generated? You may not say by the sun. Yes, they're generated by the sun, but not all of them are generated by the sun. In terms of all the ones we experience every day, not generated by the sun, okay? The studio lights are giving off electromagnetic radiation. They are not the sun, okay? Remember, electromagnetic waves are generated by the movement of a charged particle, okay? You have to have the movement, and in fact, you have to have the vibration of a charged particle. As the charged particle vibrates, it creates an electric field because it's moving. That electric field, in turn, creates a magnetic field. So we get the electric field going in one direction, and we get the magnetic field. They're both going forward, but they go at right angles to each other, okay? How are they generated? Through the vibrating, okay, through the vibrating of a charged particle. Okay, in the sun, it's because of a nuclear reaction which causes the particles to be charged. Now, from the list, write down the waves. There is nothing in this question that says you may only use something once. There's nothing that says that you may use it more than once. So what if you do need to use one of these more than once, use it. Okay, don't go, well, I've used radio waves, so it can't be that one. Be careful, okay? So now we're going into uses. Let me just take that off. And the first thing they want is used in a TV remote control. We all know you know how to use the TV remote, okay? But in the remote control, it's the infrared, okay? Nice and easy. Used to sterilize instruments in hospitals. This is a little unusual, but it's a very popular way now. It's UV radiation, okay? It's also one of the reasons why a lot of butchers have black light or ultraviolet lights over their meat. It's not to make the meat look better, okay? It's to kill the bacteria. It's to keep it sterilized. Then the one with the greatest penetrating ability. Gamma. Gamma rays have the highest frequency. Highest frequency means they have the greatest amount of energy. You've done the energy of a photon. Okay, you've done E equals HF. Okay, you did that earlier this year when you did particle nature. Okay, so E equals HF, high frequency, lots of energy. They are extremely dangerous. But at the same time, it's also the answer to 4.2.4, which asks, which one of these are used in the treatment of cancer? Gamma rays, okay? We use gamma rays because of their penetrating ability and because they kill cells, okay? They've got so much energy that when they meet the cancer cells, and remember they can't distinguish between cancer and good, which is why a lot of people do feel sick when they do radiation therapy, is because it kills the good, the bad, and the ugly, and we're quite happy with the bad and the ugly getting killed along the way, because it goes, with the energy that it has, it destroys the bad cells, okay, which is important. Then they say, ultrasound is used to obtain an image of an unborn baby. Briefly explain why X-rays cannot be used for the same purpose. X-rays have a lot of energy. They have a high frequency, okay? Because of that high frequency, the X-rays can actually damage the baby when they penetrate the mommy's tummy, okay? Ultraviolet scans, UV scans, okay? Ultrasound scans use sound energy, first of all, which is less harmful, okay? Uses waves with a far lower frequency, okay, with far less penetrating ability, so they don't do damage, whereas X-rays, because of their high energy and their penetrating ability, damage the baby, okay? They damage the baby, which is why if you ever go for X-rays, ladies, I'm sure you've had this, gentlemen, hopefully you've never had to answer yes to this question, no matter what age you are, ladies, you go for X-rays, and the first thing they ask you is, are you pregnant? Okay, you may not have X-rays if you're pregnant, not even if it's just for an ankle. You're not allowed in the room because of the danger of the X-rays, okay? Now, an X-ray photon incident on a body has a wavelength of 2,1 times 10 to the minus 9 meters. Calculate how much energy it imparts. I said to you, we're going to use E equals HF. We don't have F, but this equation has another form, which says we can use hc over lambda. C is the speed of light, h is Planck's constant, and h is 6,63 times 10 to the minus 34. Straight substitution. We're not going to try and trick you out with these, okay? So this is 6,63 times 10 to the minus 34. The wavelength was, 3 times 10 to 8, speed of light. Okay, and the wavelength was 2,1 times 10 to the minus 9. Okay, so what, when we put it on our calculator, 6.63 to the minus 34 times 3 to the 8. We're going to give an equals, divided by 2.1 times 10 to the minus 9. And we get 9,47 times 10 to the minus 17. Okay, let's just 9,47 times 10 to the minus 17. They wanted the energy of a photon, so that is joules. Tiny, 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 tiny. Okay? I think, Looney, it's time for a break.
All right.
And then we're going to come back and do some electricity.
Okay. Mindset is we are going to take a break. I wanted to do some shout-outs, but then I'll do those after. Oh, there we go. Shout-out to Njabulo, Boyza, Danuk Apiwe, Tato, Tami, Daniel. Ooh, Njabulo is on fire today on the page. Thank you so much, Mindsetters, for tuning in and for posting on our Facebook page. I see some of you do have questions. We'll go through them during the break, and we'll see you straight after this. Welcome back, Mindsetters. I'm so sorry about that. You see stuff in my ear. Yeah, people talking. Anyway, Mindsetters, you've got questions here. Tando.
Yes.
Tracy has a question. And Tando Machas is asking, what is a wavelength and what is an amplitude?
Okay, Tando, you need to learn these, okay? The wavelength is the distance between two consecutive points in phase of a wave, okay? So on a transverse wave, it's the distance between two crests or two troughs. On a longitudinal wave, it's the distance between two compressions or two rarefactions. Amplitude is the maximum displacement, in other words, how much the wave moves. So if you look at this one, how much the wave moves from the rest position, how far away from the rest position the particles move. Okay, that's amplitude.
Okay, cool, thank you. And then from up here where he asks you to clarify 3.2.1 for him. And then the question, 3.2.1 is longitudinal waves. On sound waves, longitudinal waves. Please clarify that for me.
Yes, okay, sweetie, you are 100% correct that sound waves are longitudinal waves, but look at the question. It says, name the type of wave represented in diagram 2. This is a transverse wave. Okay, so this, the way the diagram 2 is written is a transverse wave. If they had said diagram 1, that's the longitudinal wave, okay? So we've we've changed the longitudinal wave into a transverse wave, but you are correct. Sound is a longitudinal wave. Okay, so hopefully that helps a little bit.
All right. Before these mindsetters get angry at me, they just want me to say a shout out to Martinique, Mukove, Jabulile, and Lebohang. Hello to you guys. And here quickly, you see now I'm multitasking. Sean Mohlama, he says, shout out to all my classmates. I wear 10.4s from SVS. So shout out to you guys. Thank you, Tracy. Listen.
Oh, thank you.
Thanks.
I am worried about her. I've said this before. Anyway, so on to electricity, our favorite section. Okay, learn to set up a circuit as shown in the diagram below. The EMF of each cell is 1.5 volts. So we've got 1, 2, 3, 4 cells. So the EMF is actually 4 times 1.5. That makes 6 volts. Okay? Each of the bulbs, A and B, okay, has a resistance of 2 ohms. So that's a 2 ohm resistor. That's a 2 ohm resistor. And bulb C has a resistance of 3 ohms. Okay? That's all the information we're given. We've got 3 voltmeters. Let's just have a look at how this is connected. Pretend that the switch is closed. So if we take our highlighter and we go, here we go, it gets to this point, it now splits, and in fact it'll split evenly through A and B because both of those have the same resistance, so the current will just split in half between them, comes back together, off it goes through the circuit, and we're all happy. Now, I don't put any current going through the voltmeters because the voltmeters don't take the current, they measure the potential difference. First thing, calculate the effective resistance of bulbs A and B. I know the switch isn't closed. Okay, what they're asking you here is if I had to take bulb A and B out and replace it by a single bulb that would do exactly the same thing, or one resistor, what would that resistance be? Okay, so we're looking at A and B. A and B are in parallel. So we're going to refine 1 over R parallel equals resistor A plus 1 over R resistor B. There we go. So this is 1 over 2 plus 1 over 2. Hopefully we can all do this. Okay, so that gives me 1 over 1. Well, 2 over 4. Okay, just watch what I'm doing. No, it gives me 2 over 2. So much for me being able to do this. Whatever she's got, it's catchy. But remember, I want R parallel, so turn it upside down, but it's 2 divided by 2, which is 1, and 1 turned upside down is still 1. 1 ohm. Okay? Now they say to you, switch S is now closed for a short time. Determine the reading on voltmeter V1. We've already done that. Okay? We have already determined the reading of voltmeter V1. V1 sits over the cells. There are 4 cells. Each of them has 1.5 ohms, but we need to write it down. So V1 is going to be 4 times the 1.5. So it's 6 volts. Then they ask you, and I really didn't give myself enough space, the reading over V3. Okay. Now comes the fun part. I really did not give myself enough space. This has an effective resistance of 1 ohm. Okay, here's 3 ohms. We need to know the current in the circuit in order to get V3. Okay, you are more than welcome to use ratios. I just think it gets difficult, and the way this splits up, and let's not even go there. Okay, don't do it. So what we're going to do is we're going to work out the total resistance first of all. And I think what I'm going to do is I'm going to do it at the bottom because I didn't leave myself enough space. Okay, so the total resistance, so we need R total, which will be my parallel section plus C, which is in series. So it's 1 plus 3, it's 4 ohms. I'm going to work out total current. So this is 4 ohms. My total voltage was 6. So my total current is 6 divided by 4, which makes it 1.5, which means the 3 ohm resistor is also getting 1.5 volts. Okay, so RC is going to be V3 divided by I total. So this is 3. This is 1.5. And we're going to go 3 times 1.5, which means 4.5 volts. Okay? 4.5 volts. This is one of those times when you really just have to be quite logical about it. So now what we can also do is I'm going to go back to my diagram. And I'm going to go, okay, well, I am going to go back to my diagram, even though. So that worked out to be 4.5 volts. My current, should I not like scribble? I total is 1.5 amps, and my switch was closed. Okay? I'm writing in the information that I've worked out along the way because I may or may not need it. Okay? It's really important that you do this grade 10 and you get into the habit of writing these things down, because particularly with electricity questions, they start to become quite complicated and you have lots of extra things added in them, and then you lose track of what information you know and you're going to get yourself lost. So be careful. All right, so we said V3 is 4.5 volts. A bit of a horrible mark allocation, but that's okay. Calculate energy transferred, W, in the light bulb in 3 seconds if the current in the circuit is 2 amps. Okay, well, this is an interesting question because the current in the circuit isn't 2 amps. Okay, the current in the circuit is 1.5, but take it as it's given to you. Okay, you have to calculate energy transferred. Now, they want W. They're telling you in 3 seconds if the current is 2 amps. You have a couple of equations. You know that V equals W over Q, and you know that I equals Q divided by time. Okay? We want W. I know V. It's 4.5. We just worked it out. I need Q. I can work Q out because I know I and I know T. Okay? So this is 2Q divided by 3. So Q equals 6 coulombs. My V is 4.5. We want W. That's 6. Okay? So W becomes 6 times 4.5. Okay? So let's just work that out. 6 times 4.5. We get 27. So W equals 27 joules. Okay, now this is obviously a typing mistake in the paper, okay, because you know we just worked it out. The current isn't 2 amps, it's 1.5 amps. Please use the information given to you, okay? Don't go, and I know it freaks you out a little bit, don't go, well, I've just worked out current to be 1.5 amps. They won't carry that 1.5 amps down into the next question because they gave you a current to use. Use that current. Please be careful with that grade 10s, okay? It's easy for this sort of mistake to come into a paper. It's very easy. Use it as it's given, okay? Then, all the light bulbs are now connected in parallel. How will the current in the circuit be affected? Write down only increase, decrease, it remains the same. Very important for you to remember. When I add resistors, which is what a light bulb is, in series, one after the other, total resistance increases, okay? Which then will mean the current will get smaller. When I add light bulbs in parallel, one on top of each other, total resistance decreases. The more resistors you have in parallel, the smaller the resistance in total. If you have a small total resistance, you have a greater current. Current gets bigger because the voltage stays the same from the cell. Okay? So my answer here would be that your current increases. Okay? Very important. Looney,
Yes.
do we have questions? She's
Hold
just
that
going to
thought.
refresh the page
Yes.
because she's busy doing other things. Okay? Guys, with circuits, you're probably only going to get one circuit in your exam. Practice, practice, practice. Okay? Also, if you look carefully at the waves, particularly here, can you see I put like lots of little subscripts? T, P, C, 3. I'm naming what voltage and current I'm using. Okay? It's like calling Looney and I are both girls, but if you want to differentiate between us, you need to call Looney by her name and you need to call me by my name, which is what the little subscript is. It's name. Okay? Now she's looking like she's got a question for us. So let's quickly see if I can help.
Okay, okay. Mukova is asking, can I please know how the X-ray can interfere with the health of the baby?
Because X-rays have a very high penetrating ability. They have lots and lots of energy, and that energy damages the growing cells of the baby. Okay, so when they interfere with the baby cells, remember baby cells are very delicate. So they come along and they actually damage the cells of the baby. So they can cause deformities and all of that sort of stuff.
Okay,
Yeah.
and then Lo was asking for the answer for 4.2.4. Would you be able to go back?
It was gamma.
Gamma.
Was
Okay.
gamma rays, the treatment to cancer. It's gamma rays, high penetration. Remember, we want the high penetration because they got lots of they got a high frequency, lots of energy, damage, and kill all the bad cells. Okay?
And then, yes, this name I can't pronounce, Keyur Danuk, is asking to explain question 1.2. He says, could you please explain it?
1.2.
Yeah, it doesn't understand.
Okay, let's find 1.2 again. Okay, 1.2 here was draw the shape of the resulting wave. Okay, Sweet Pea, you've got two waves that are interfering with each other. Okay, crests are meeting crests, troughs are meeting troughs. That makes it constructive interference. It increases the amplitude of the wave, which is why I drew a wave with a bigger amplitude. Okay, here there are two waves on the diagram, on the original diagram, two wavelengths. So I have two wavelengths on my diagram. And then this amplitude, which I've just moved, look at that. That A plus B is because A's amplitude gets added to B's amplitude because it increases. Okay? And I don't think, unless it's really short.
No, I don't. No.
Okay, guys, that's all I have time for. Next week, we're going to do some more chemistry. We're going to pick up on some more chemistry. I know some of you asked about equations of motion. Next time, 2 weeks' time.
Okay, cool. Mindsetters, thank you so much for tuning in. All the best for your exam preparation. Remember, we're going the distance together and we're going to pass those exams. From us, mwah, goodbye.